Today I'll explain slope percentages in simple terms, discuss how planners control slopes. For example, many places, including my home in Goa, prohibit construction on steep slopes. And we'll show you how to analyze slopes using GIS and manual methods. I want to stress on some common misuses of slopes. For example, a dangerous mistake I see many architects and engineers do of averaging a whole site's elevation change to claim a slope is a certain value, when in reality, parts of the slope can be very steep. By the end, I hope you can share my concern that accurate slope analysis is literally a life and death matter. This is part two of a two-part uh, lecture on slope analysis for environmental design and planning. I would highly recommend watching part one, which discusses how one can even understand what the elevations and slopes of a site are. In everyday terms, the slope or gradient between 2 points is how much one point is higher or lower than the other relative to the horizontal distance between them. We usually express slope as a percentage, sometimes called as percent grade or percent slope. The formula is very straightforward. Slope percentage is the rise divided by the run multiplied by 100. For example, if you go 1 meter up over 4 meters of horizontal distance, that's 25% slope. A 45-degree slope is technically a 1 meter rise over a 1 meter run and equates to a 100% slope. As the slope angle approaches vertical, the percentage goes towards infinity. A cliff, for example, would have an infinite slope percentages, and perfectly flat ground has 0% slope. Engineers and planners particularly like to write slope in percentage, not degrees. A 25% slope is around a 14-degree angle if you prefer that. We do this mainly because it's so much easier to do the math, and we sometimes have to do a lot of math. To visualize this, a 10% slope is a moderate incline. A wheelchair ramp is around 6%. A 25% slope is so steep that most vehicles, even off-road vehicles, cannot climb it. Steep slopes must be protected and regulated because they pose risks, the most obvious one being landslides and erosions. This picture is of the catastrophic landslides that hit Kerala, South India 2 years ago. Slopes impact water flow, drainage concentration, and also generally form part of densely forested natural areas and wildlife corridors. Not to mention that it's much more difficult to construct on a slopy land. Some of my engineer friends may see this as an opportunity. I veer with caution. But to ensure safety and environmental protection, laws sometimes prohibit development on slopes above a certain gradient. In the state of Goa, for example, since 1997, we were the first place in India that banned development on any slope steeper than 25% and needed strict permission for any construction on slopes steeper than 10%. Closer to home in the East Bay region of California, local authorities have very robust hillside regulations. In Oakland, Section 172550 forces you to take a permit if any slope exceeds 10%, and any land disturbance that could even doesn't have to be construction on a slope exceeding 20% is only allowed with prior permission in emergency situations and only to safeguard human life or property. So it's really strict. In Berkeley, any land steeper than 8% cannot even be used as open space. So the East Bay, because probably of how its topography is rather strict with development on the slopes. Similarly, in Goa and the south of India, laterite stone has a tendency to landslide down, and therefore over there as well we have rather strict land regulations. Goa went a step further and made an attempt to show the steep areas. They tried to follow a practice of clearly defining and measuring areas above 25% slopes. But how exactly do you do this? We'll cover it in more detail as we go ahead, but a good practice is to use high quality survey data to map all areas above the threshold. The Goan planners used the Survey of India 10-meter maps, and what you see in these green zigzag lines is the areas that they marked as no development slopes. Now, I have thoughts, and most researchers do, about the Survey of India maps. So I would highly recommend going back to part 1 to understand that. Recent amendments to law now require that when someone submits a development proposal on a hilly land, they must provide their own slope analysis of the site. This too aligns with what we see in Oakland and other places in the Bay Area. In Goa's case, even though the state created overview maps, a specific project must still include their own detailed slope map to ensure it adheres to a 25% limit. In other words, you can't eyeball a slope, you must do the analysis and it will be scrutinized. Now, given such regulations, how should one correctly analyze slope on a site? There are two modern approaches, a GIS based slope analysis and a manual cross-sectional analysis. Both are useful, and using them together is maybe the most ideal. But before understanding them, let's go back to the 1930s and discuss what's called the Wentworth method of slope analysis. On screen, you have a contour map. Every contour is at 1 meter intervals from one another. The first step in the Wentworth method then is to plot a grid over your contour map and set a certain minimum size for the grid. In this case, I've taken a 10 meter by 10 meter grid over it. Now, using this, I can then count how many contour lines fall within each 10 meter by 10 meter. If I'm talking about a 25% slope, and if there's a 4 meter rise, that is 4 contour lines falling inside one of my grid boxes, that portion of the site is a 25 meter slope. And so I can just start coloring in using different colors for very steep, moderate, and mild slopes. And this is how you spatially understand where the slope where different parts of the site and how steep they are. It's akin to eyeballing the contour lines and seeing, oh, these are close by together, therefore this is a steeper part of the site, these are far away, therefore this is a less steep part of the site. Modern GIS have tools that automatically take in a contour map or a DEM, digital elevation model, and compute the slope at every location. ArcGIS has, for example, a slope function. Internally, it uses a model very similar to Wentworth called the planar model. It makes a grid, identifies different points in each grid, and sets an elevation of those points. Look at the box on top. It then calculates the steepest rate of change in elevation from that point in the grid to a point in the next grid. Technically, the tool fits a small plane or a surface and finds the slope of that plane. The result is a new layer where each cell's value, each dot, each gridded value is in degrees or percentage of the slope. If a particular 10 meter by 10 meter patch of hillside rises 3 meters from its lower edge to its higher edge, the tool will assign that cell a slope of 30%. These slope calculations are very detailed, and therefore a slope map shows how steep every part of the site is. Steeper areas can be highlighted in red, moderate in yellow if you use a color ramp. This GIS slope tool is essentially automating what a human would do by using the Wentworth method or looking at a contour spacing. One advantage of the GIS approach is it's very systematic and covers every corner of terrain, while a manual approach might miss. However, it's only as good as the data you feed it. If your DEM is too rough or your base data has errors, the slope map will inherit those. The sectional method is more old school but also very insightful. Here you draw various cross-sectional profiles through the terrain and measure slopes on those profiles. Think of it as cutting a hill vertically along a line and then looking at that slice from the side, like a side elevation of the ground. If you have a contour map, you can do this by picking lines across the site. Ideally, you pick the steepest path and also several paths in different directions and different portions of the site. And then notice the elevations where the line crosses each contour. Plot these elevation points against the distance to get a side-on profile of the hill. See this example that I found from Santa Clara County. They forced you to cut 4 sections in 4 different parts of the site, A, B, C, and D. And we can measure the slope of each of those different segments of each of those different sections. Between each of those sections, the difference between the top elevation, top level, and the bottom level between x and y is x, and the vertical difference is, and the horizontal distance is y, then the slope becomes x by y. Doing this for multiple segments shows you where the hill is the steepest and how the slope varies. This method is what planners did before computers and is still a great way to double check GIS. Sometimes looking at sections helps to spot anomalies in the data too. Sometimes a contour line may have been misplotted, the profile may look unexpectedly jagged. In practice though, for a thorough analysis, one would use GIS to flag all areas over your threshold. Therefore, you get a spatial map of the restricted and regulated areas, and then also take many representative cross sections to communicate how specifically the slope changes across several parts of the property. I foregrounded this before, but misusing slope calculations can lead to dangerous or unethical outcomes. One common misuse is calculating a slope for a large site by only using the highest and lowest point and ignoring everything in between. This gives an average slope over the entire site, but it can severely underestimate the steepness of any particular section of the site. Yet I constantly hear architects talking about average slope, average slope. This is not uncommon. I found this in our survey textbook. Look at the levels of this site, but if this entire portion of land calculated on an average, it may be fit to cut. Are you going to cut these very steep cliffs and put future residents of your own development project at risk? As we speak, there are allegations back home in Goa that property is zoned as 25% plus slopes in the plan, where GIS analysis also shows them as 25% plus, and the government has given a report on the basis of their slope analysis saying that they are within permissible limits. Allegedly, these decisions are being taken on the basis of a single section cut between the highest and the lowest point of the site. Look at this one on screen as an example. Remember, some of you will be in the position of planners. Please make an effort to regulate strictly. Regulators usually don't mean the entire site because plot boundaries are artificial and created by humans. Nature does not adhere to plot boundaries. Any portion of the land that's steeper than the threshold percentage should not be disturbed. A few rare regulations like New York do call something average slope for certain calculations. For example, determining FAR or open space requirements, but even those define it through a formula that forces you to draw multiple sections and take multiple slopes on different parts of the site and not just the highest and lowest. Further, the New York regulation explicitly excludes extremely steep areas like cliffs from the average slope because including them in the average makes the whole site seem steeper, and those parts of the site anyway can't be developed, so they're left out to give project proponents some fairness in using the rest of their site. In short, if you see someone just taking the highest and lowest elevation of a big site and dividing it to get a percent, be very skeptical. This is almost always an oversimplification, if not an outright attempt to bypass laws and regulations. A legitimate slope analysis will either what? Produce a map highlighting all areas above a critical threshold slope, showing, for example, that 30% of the site is off limits because it's steeper than 25% slope, or at the minimum, detail the range of slopes present through multiple sections, not a single value. It may say the site has areas ranging from 10 to 40% slope with an average of 22%, but then the regulation will still disallow using any of those areas that exceed 25% slope. Finally, to conclude, I want to recap things from the first and second lecture. Firstly, contour maps and DEMs are only as accurate as the source data. Always independently check if you have a doubt. Slope percentage is a straightforward concept. It's the rise over the horizontal distance multiplied by 100, but applying it to real terrain requires detailed analysis. Accurate slope analysis is mapping out exactly where slopes exceed the limits, typically using GIS and cross-checking with manual sectional methods. Oversimplifications of slopes, especially highest to lowest trick, can completely undermine the interest of slope regulations. And if a dispute arises, go back and do an independent, fresh survey. Thank you for listening to me talk about slopes. I hope this is interesting, enlightening, and gives you some understanding on how planners should be doing it. Thank you.